Hey, my name's Katherine. My mentor was Dr. Marie Chaim, and for the most part, we studied integrating Gα12 signaling with AI-enhanced imaging in glioblastoma. And I'll dive into every part of that sentence in a moment. So, for a brief table of contents and agenda, I'll be going over an introduction, material and methods, results and discussion for AI and ML, results and discussion for biology, some integration talk about how we can put biology and machine learning together, and then a brief conclusion. So a brief introduction is glioblastoma multiforme, or I'll probably refer to as GBM, is one of the most aggressive brain tumors, and there's only 12,000 cases a year in the United States. Pathology-wise, it has really rapid growth and cell death, which leads to poor survival. On a imaging landscape, it's very abnormal cell and vessel growth. So our focus was Gα12 and Gα13 signaling, which are G proteins, and they drive invasion via GPCR signaling, which is a fundamental biological mechanism. If someone has taken an introductory biology course, you've probably heard of it. It's just a way for intracellular communication. These pathways affect proliferation, migration, survival, and the issue with current imaging is that it's really lacking in terms of this integration between biomechanisms and imaging. So our aim is to review Gα12 and Gα13's role and design an AI ML imaging tool combining biomarkers in a patient-friendly interface. On the right is kind of what a imaging of a GBM would look like. On top is an MRI, and then on bottom is more histopathology. The black arrows are necrosis, and so you can really see how there's a lot of centers of necrosis in glioblastomas. So methods and materials, I'll go through this pretty quickly. Nature Editorial, MDPI, and PubMed are all huge literature databases that I used. TCGA is a large genomic proteomic database and it's limited to GBM samples. So I use this as a data set within a wider data analysis software. On the left is a statistics infographic on TCGA and just how much data it has. It has 2.5 petabytes of data and has 33 different tumor types. So it was really, really helpful. Methods continued. We have an array system used also through the software, which is called GlioVis, the second one I listed here. GlioVis is kind of a data visualization tool, as you can see on the left. It analyzed mRNA expression of all those genes I listed. It studied correlations and drafted really helpful tables for me. So this is really helpful in terms of analyzing GBM statistics. In that system, you can choose what kind of arrays, data sets, and things you want to pull from. That's the first one listed, which is HGU133A. It's a microarray, which is a biological tool, and it kind of analyzes transcripts and strengthens statistical correlation for me. Pearson correlations is a normal, like correlative statistical method to look at correlation between two things. In my case, was genes. And then Claude was the last part of my research, which assisted me in drafting an AI and ML framework design, which I'll go over in a moment. So the present issue with AI ML neuroimaging is that we have really limited accuracy and reliability. The challenges here are external validity. These softwares are trained on single data sets, so it really lacks diversity. So then when it goes into the real world and it has this very heterogeneous kind of tumor data set, it really doesn't apply anymore. So this homogenized processing misses variety in clinical imaging. So like different patients, different scans, different qualities, and different ethnic groups might have different reactions to tumors as well, and it doesn't really account for that. There's also a lot of patient trust issues in that there's AI bias from underrepresented minorities. And there's also evidence and statistical evidence that there are higher error rates for minority groups. So there's a pretty big laundry list of concerns here that we're trying to address, and hopefully that can get resolved later as research goes on. Our approach is to have a patient-friendly model that allows for disclosure of race and ethnicity, but also personalized solutions. So the current imaging with biomarkers is that early on, its accuracy is pretty small, but later on, the accuracy is actually pretty good. So we think that it just needs more development to be able to be a diagnostic tool instead of just being a treatment tool. In terms of machine learning strength, it's pretty good. It rapidly processes data strengths and supplements MRI. And there's some evidence on this as well and how machine learning can supplement imaging. I just don't think it's at full-fledged capacity yet. But our goal is to basically integrate biomarkers and artificial intelligence machine learning to have a stronger, fairer, patient-centered diagnostic tool, which could resolve some of the patient trust issues while also solving diagnostic issues that might be too homogenous at the moment. So now as we dive into biology, I basically studied what my mentor studied a while ago. I looked over how Gα12 promotes invasion in glioblastomas through GPCR and this other pathway called RhoA that has some complicated processes. But overall, the main point is that increased Gα12 expression led to worse survival. Then knockdown, which is a kind of like biological cell method reduces invasion by 47%. Basically, it's like getting rid of one kind of expression. So when we got rid of Gα12 expression, we saw reduced invasion, which is good. So this KD also downregulated 812 genes and then let us know kind of what the stem markers are. And so the overall conclusion was that GNA12 and this other gene axis is a driver of GBM invasiveness. The other gene axis, which is THBS1, is like a cell growth factor. So when they work together, we see that it does assist in GBM invasiveness, which we do want to avoid. So it gives us a lot of insight as to what oncological treatment we can start pursuing to kind of stop GBMs from growing. This is a really brief table I combined of like all the statistics. It's really comprehensive, so I don't really think there's a need to go over it right now, but this is included in my paper. As we go over GNA13, so GNA12 and GNA13 are analog genes. So when I researched one, I said I might as well research the other. And it ended up being a really great uh, way to analyze. So GNA13 is the opposite of GNA12. It acts as an invasion suppressor. The key findings are that when GNA13 decreased, or GNA13 was less present in GBM tissue versus normal brain tissue. And when we increased GNA13, there was longer survival and less invasion. So this is kind of like the opposite pattern that you can think of with GNA12, which I thought was super interesting because they are analog genes, but they have really opposite patterns. Knockdown in this case related to increased ERK phosphorylation, which led to expression of tumor suppressors. So I think that also gives a lot of insight into how two genes who seem pretty similar and two proteins who seem pretty similar might have very different effects on kind of abnormal growths. Overexpression suppresses ERK and then increased FOXO3, which reduced invasion. So the conclusion is that GNA13 restores control over ERK pathways, which is a signaling pathway, which limits invasivity, which I think was really interesting. This is a correlation graph of GNA12 and GNA13. It's weakly correlated, but statistically significant to display that there is a negative correlation, which is what we saw earlier. A brief comparison is, I already went over this a little bit, but GNA12, GNA13, GNA12 is pro-invasion and reduced survival, while GNA13 is anti-invasion and suppresses some of the signaling pathways that might have led to excess cell growth. The net effect is that GNA12 and GNA13 have different invasiveness and expression patterns. The therapeutic insight here is that targeting GNA12 suppression or GNA13 restoration could improve GBM treatment. So I think that's really where the capacity for treatment lies and kind of where the imaging should step in and kind of analyze that. And with those biomarkers and biological mechanisms, that could be really helpful for understanding the prognosis of someone who might be having a GBM. Integration, so biomarker potential, the current example with gliomas, which is a lower grade form of glioblastomas, is a form of MRI. It's called AMI proton transfer weighted MRI, so APTW MRI. It's a standard MRI that can detect molecular features. It can identify things like IDH1, 2 mutations, Ki67 index, but these things are slightly different from G proteins, although they are really significant biomarkers. The future opportunity is that we can integrate biomarkers and AI/ML for faster, more efficient, and more accurate diagnostics. But limited data sets right now and a lack of integration is a pretty ongoing challenge. On the right is how APT MRI looks like against a regular MRI. So you can see it really gives like a lot more like dimension and contrast. And then in an actual scientific sense, like in a lab sense, you can there's like a water technique that you can use to contrast biomarkers. Our interface is a dual interface AI ML imaging system. On a physician end, you can upload diagnosis, genetic data, test results, and medical history. And then the AI processes biomarkers. On the patient end, it's an interactive body model to visualize tumor growth and progression. And so it summarizes reputable resources to explain diagnosis and has the option to ask AI general questions. So the goal here was obviously to combine scientific rigor and a patient-friendly design. You can kind of see that on the right. It's a little snippet of like the dashboard and kind of the important part of my framework that I made using Claude. So that's kind of what it looks like. Really brief conclusion. Uh, mostly said this throughout the speech or throughout my presentation, but GNA12 promotes invasion, GNA13 suppresses invasion. Together, we can have biomarkers and therapeutic targets for GBM, and current imaging and biomarkers is in progress, but GBMs are still underserved because the only example I could find was in gliomas. The need is patient-friendly AI ML imaging, but the future has combining molecular insights, which is more accurate, accessible, and personalized care. My TSI experience was a really great time. I had a lot of opportunities with my mentor. She gave me so many resources. Gliovis is truly one of the greatest softwares I've encountered. It solidified my passion for science and research in general. I've been a very interdisciplinary person, and so science was always something that I've been curious about, and I'd love to go into medicine in the future. But it was like I needed a research experience to kind of solidify that, and that this was really great. I had a huge connection with my mentor. She lives in Brazil, so we met over Zoom. But we found a lot of similarities with each other and how passionate we were. Going along that sense, a research community that's really passionate was something I really gained from this. And the amount of connections I've made is truly the best experience in that I probably could not have known so many people who are so passionate and so talented in so many fields had it not been for TSI. So that's my presentation overall on pretty much everything.